This is chapter 14 in Geography 115's textbook, the textbook we're using, which of course is Extreme Weather and Climate by Arendt and Sampson. And I split this presentation into three parts also. There's a 14A, 14B, and 14C. And this chapter is all about weather forecasting. Hopefully we can sort out some of the mysteries for you about how meteorologists do their work, operational meteorologists. So this chapter is going to cover how weather data is acquired and how it's analyzed, weather forecasting tools, weather forecasting methods, predicting short-term and hazardous and severe weather events, and also predicting long-term weather and climate patterns. That's what the entire chapter will cover. So basically it's like this. Weather forecasts are obviously useful because they're issued to save lives, property, and crops. The National Weather Service does a tremendous job of doing that for the United States. They issue timely advisories, watches, and warnings in order to make sure that they save lives and protect property. That is the mission of the National Weather Service. Forecasting is both a science and an art, and it's obviously challenging for a number of reasons that we have time to explain and some we don't have time to explain. Inaccurate forecasts and public complacency can both cause problems. Now, all over the world, weather conditions are observed, both on the surface and aloft. There is tremendous international cooperation in the gathering, the acquisition of weather data. Surface observations are mostly at airports. We discussed how that was done with the ASOS instrument array. Some observations are from ocean buoys, and I showed you that in chapter 13, and also some are from ships. Upper air observations are from radiosondes, from aircraft, and of course from remote sensing satellites that orbit the Earth. All this data is collected by a branch of the National Weather Service, which is called the National Center for Environmental Prediction, or NCEP for short. NCEP analyzes the data, prepares the maps and charts of current weather, and maps and charts for future weather based on mathematical modeling of atmospheric properties. Individual National Weather Service forecast offices have access to all this information that NCEP puts out, plus their own Doppler radar data, because the WSR 88D Doppler radar is co-located with all 119 National Weather Service offices. The current data and the forecasts are disseminated by National Weather Service by way of the internet. Each Weather Service forecast office has a website. The specialty offices like the National Hurricane Center, the Storm Prediction Center, they all have their own websites. NOAA Weather Radio, commercial broadcast media, of course, radio and television, and also through social media increasingly. That's how forecasts, watches, warnings, advisories are issued by the National Weather Service. Short and medium range forecasts, advisories, watches, warnings, and a variety of other products are also issued by local National Weather Service offices. Special units like the Storm Prediction Center, National Hurricane Center, I just mentioned those, they focus on severe weather and hurricanes respectively on a national scale. In order to get the proper definition of watches, warnings, and advisories, I highly recommend that you read the focus box on page 401 regarding those topics. Now, all 119 National Weather Service offices have a computer system to integrate all of this data so that it's useful for forecasters. It's a workstation called the Advanced Weather Interactive Processing System, or AWIPS for short. The ASOS observations from airports and the Doppler weather radar is also processed by AWIPS, but those are actually, that data is actually processed even before the forecaster sees it and has put it in a form that he or she can take a look at. So this is an example, this photograph, figure 14.1 of the AWIPS computer weather station workstation that you're going to see at any of the 119 National Weather Service offices across the United States. This processing of the data through software with predetermined formulae called algorithms alert the forecaster to impending weather situations. Other software will break the forecast of weather elements down into spacing on a map as low as 2 kilometers, which is really quite astounding when you consider that. About 1.5 miles resolution. There are charts called meteograms, and on the right is an example of a meteogram that shows how several weather elements at a ground station have changed over time, and can also show how these elements are expected to change over time in the future, up to 5 days in advance. There are also soundings of the upper atmosphere from the radiosondes. We discussed that in Chapter 1. And also wind profilers and satellites are used to profile the upper levels of the atmosphere. So this is an example, 14.3, of a meteogram of a 2-day forecast for St. Louis, Missouri for November 19th, 2007 through November 21st, 2007. You can see precipitation projections, 500 millibar thickness. That's instrumental in helping to forecast whether it's going to rain or snow. 850 millibars, that helps us to forecast surface temperatures, how close the temperature and dew point are expected to be together, and also the sea level pressure. Sorry for the graphic being in the way there. That seems to be happening a lot. On the left is a radar image from Melbourne, Florida, showing a hailstorm that caused $60 million in damage. And also on the right, figure 14.4 is a sounding from a radiosonde for Pittsburgh, Pennsylvania, which shows you how the temperature and dew point are kind of stuck together, and then they separate when the parcel goes aloft a little higher above the surface. You can also see the wind barbs on the right indicating wind speed and wind direction. Looks like consistent southwest winds above about the 900 millibar pressure surface there. Let's talk a little bit about numerical weather prediction. And this is an interesting story. We know the properties of the gases that make up the atmosphere. So about, let me think here. This would have been about 80 years ago or so, maybe 90 years ago. Mathematicians at a prestigious university, I think it was MIT, decided, well, you know what? We know the properties of the atmosphere, so with highfalutin mathematics and enough mathematicians in a room, we should be able to calculate what the properties of the atmosphere are going to be like at some time in the future, like maybe a day or two in the future. But they realized that they would have to have rooms and rooms and rooms of mathematicians doing these calculations, and by the time the calculations were complete, the period of time that they were forecasting for would have passed them by. And they dreamed of the day that we would have high-speed computers to do this. Well, guess what? Now we have high-speed computers to do this. This is where numerical weather prediction comes in. Weather observations are transmitted to INCEPT. They're fed into high-speed computers to produce synoptic charts of current weather. That's the analysis part of numerical weather prediction, looking at current weather, figuring it out. Those same computers, which are loaded with these mathematical atmospheric models that previous meteorologists only dreamed of, then perform what we call numerical weather prediction. Each equation is designed to solve the forecast problem every single day. And this forecast problem is solved for small increments in time going forward and for a large number of locations, which we call grid points. Each equation is solved for as many as 50 vertical levels of the atmosphere going up from sea level for time steps in the future in 5-minute increments. So get your mind around this. The numerical weather forecast done by computers forecasts in advance 15 days in 5-minute increments for 50 distinct levels of the atmosphere above sea level. That is really quite amazing. The charts that are spit out of the computers that result from this are called prognostic charts, or progs, which give us the weather expectations for future increments in time. And each model is designed differently from the other, both mathematically and spatially. For instance, some models cover only North America, other models cover the entire northern hemisphere, so there's a difference in the resolution of these prognostic charts. Forecasters use these progs as guides to predicting the weather, which is ultimately what you look at when you wake up in the morning and look at the weather forecast. Now, let's look at different numerical mathematical models to find out what the chart looks like and then find out what the result was ultimately. So this figure from your book, 14.5a, shows the WRF, the Weather Research Forecast in North American numerical model. The WRF-NAM model. This is a prognostic chart issued for the time of July 12, 2006, which was issued 48 hours before the period of time that this chart is forecasting for. This model has a grid spacing or resolution of about 12 kilometers. So here's the WRF-NAM model showing what the upper atmosphere was supposed to look like at 7 o'clock p.m. Eastern Standard Time on July 12, 2006. Next is a model called the GFS model, the Global Forecast System model. This is 14.5b. This is the GFS model forecast for July 12, 2006 at 7 p.m. Issued again 48 hours in advance, issued on July 10th for 48 hours forward on July 12th. This model has a grid spacing resolution of 60 kilometers. So in theory, you would expect the previous one, the WRF, to actually do a better job of forecasting for North America because it has a grid spacing of 12 kilometers, while the GFS model has a grid spacing resolution of 60 kilometers, and it covers the entirety of the Northern Hemisphere. But check this out. This is the actual result. This is the analysis of the 500 millibar surface for 7 p.m. EST on July 12, 2006, and it's quite evident when you look at that GFS actually had a better forecasting result than the MRF did. So it's a very, very interesting than the WRF NAM, I mean, the North American model. So sometimes some charts are simply better than others. That's just how it works. Now, let's talk a little bit about why national weather forecasts aren't perfect. The mathematical models make assumptions about the atmosphere which don't always verify. The models that predict weather for a continent may not properly take into account events outside the spatial range of the model, so errors tend to creep in. For instance, if the North American model is forecasting for North America beyond the adjacent ocean, it may not take into account events that are happening, say, way out in the Western Pacific near Japan, and that can make a forecast go awry by the time that blob of air moves to North America. Models which predict weather for a hemisphere aren't fine enough to deal with the mesoscale, because remember, they have a 60-kilometer resolution, while the ones that deal with the continent maybe have a 12-kilometer resolution. And of course, meteorologists live by the models and die by the models, because if you hang your hat on that science and it goes awry, well, you know, that's the way it goes. Now, it's getting better all the time, I might say. People always joke about weather people, say, those people never get it right. But actually, the science has really improved. Some models have been developed for mesoscale forecasting, such as a model called the MM5, which has a grid spacing of only a half a kilometer, which is really good for severe thunderstorms. Now, in spite of thousands of ground-based weather observations and satellite observations, there are parts of the world that are data sparse. Those gaps can cause problems for the models, but the gaps are filled in to some extent by data from those satellite sensors aloft. Even with better observing techniques and better computer models, there are countless small, unpredictable atmospheric fluctuations that fall under the heading of chaos that we simply do not yet have the capability to detect. There is a method called ensemble forecasting, which is increasingly used now, and I briefly referred to that when I talked about hurricanes in Chapter 13. The computers tweak one or more of the initial variables or elements that are observed, and when they put them in the model, they run the model several times to see where the majority of the solutions end up. The less agreement with the solutions, the less predictable the weather. The more agreement with the solutions, the more predictable the weather becomes. So figure 14.7 is actually an ensemble 500 millibar forecast chart for July 21st, 2005. It was issued 48 hours before that time. But the idea then is that the scientists examine where most of the model solutions lie in order to figure out future weather. The blue lines are at the 500 millibar surface, 5,790 meter contours. The red lines are the 5,940 meter contours. So the blue lines would indicate troughs of low pressure. The red lines would indicate ridges of high pressure. And the green line is the 25-year average, which defaults to climatology. The kind of a plot that results from the running of an ensemble run of the model is often called the spaghetti plot, just because the way the lines are arrayed across the chart. This ends the PowerPoint for Chapter 14A.